Right, so welcome to Math 150 Multivariable Calculus. You should all have received an email from me basically with some general information about the course, with information about the homepage and stuff like that. If you did not get that, please let me know. I just emailed everyone again today using the information on Glow. For the most part, I'm not going to use Glow. I'm going to have everything run off my homepage. The only thing Glow is going to be used for is for submitting homework, so that this way, everybody can just submit their homework. Homework is due at the start of class. You should be writing neatly. You should make sure that you have lighting that is good enough so that people can read what you're doing. If you want to type up your homework, that's absolutely fine. But basically, today I wanted to just talk a little bit about the course mechanics and then leave it as an opportunity for you to ask some questions if you have them about the class in general, about the major classes at Williams in particular. That's also fine. And then we'll start the material in earnest on Monday. So this is multivariable calculus, so you should have seen Calc 1 and Calc 2. It is quite fine if it is a little bit rusty, if it's been a while since you've done stuff like that. Hopefully people will be willing to speak up through Zoom. Does anybody want to tell me what their least favorite integration technique is? Everybody likes everything equally. I can use anything in this class.
Partial fractions.
Partial fractions, thank you. So partial fractions will not be in this class. So I'm not going to do partial fractions. I'm not going to be doing, for the most part, trigonometric substitutions. I want to focus on, for the most part, what are the new ideas in multivariable calculus. So mostly when we need to use results, we're going to be doing U substitution or integration by parts. Those are going to be the most common techniques. If it's been a while since you've seen the washer method and stuff like that, don't worry, we're really not going to be using that. I want to focus on what's new in multivariable calculus. What are the new ideas? What can we use this to solve? So a lot of that is going to be extending what you've done in one dimension and seeing where are things different. So for a lot of things, it's going to be very similar in several variables as it is in one variable. And other problems, it's going to be a world of difference. The biggest thing is that when we are in multivariable calculus, we have much more freedom for limits. And this is where I was hoping that I would be able to have things working. I will try to do it this way. So in one variable calculus, we have the real line over here. Here is 0. How many ways are there to approach a point in one variable, in one dimension?
2.
Essentially, there's 2 ways. You can come up from the negatives, you can come down from the positives, and that's it. In multivariable calculus, it's going to be very different. How many ways do we have to approach the origin now in multivariable calculus?
A lot.
A lot. So it's a lot. 2, 3, a million, a billion, infinity. A lot is correct. Let's be a little bit more specific about how bad is a lot.
Infinite ways.
Infinitely many. So there are the most popular, top 10, coming down the axes, those are great. You could come in at an angle. You could come in as a parabola. You could try to do something a little bit more exotic and maybe you do some kind of spiral coming in. You could do maybe some kind of Jackson Pollock, getting smaller and smaller and smaller. All of those are going to be fine. So when I first started teaching multivariable calculus, my kids were at the Children's Center on the college, and I had everybody in their preschool class make an individual scribble like this for all of my students. If you've seen, the Karate Kid, I think it's the second one where they go, The Secret of Miyagi Karate. The secret of multivariable calculus is that you have to be able to handle all possible paths. And these strange scribbles where you're coming in and doing God knows what, and eventually coming to the point, we have to handle that as well. And so we need a little bit more stronger techniques than you have in standard one-dimensional calculus to handle something like this. So this class is going to operate at several different levels. At the most fundamental is to make sure that you have an understanding of the techniques of multivariable calculus so that you can take derivatives and you can do integrals. A lot of this is very straightforward if you know Calc 1, Calc 2. So it takes less than a minute to teach you how to do partial differentiation, and that's a core part of the course. What's going to take a little bit longer is to give you some justification as to why it's true. Why does this work? What do you have to be careful about? And so I am going to do some of that. Some of that will be done in the lectures. Some of that will be done in the videos that you watch. But I am not going to hold you responsible for doing these proofs. This is a math class. You should know that it is a math class because we can prove things. And that there is a justification for everything. But on exams, I am not going to require you to be able to do that. This is a good time to talk a little bit about the grading metric. So homework is 15%, midterms will be 40%. There will be at least 2 or 3 midterms. I will drop your lowest midterm unless you tell me otherwise. So I'm going to just assume everybody wants the lowest midterm dropped. Final is the rest. You can change the grading scheme and have 60% of your score be a 92.5, right on the boundary of an A minus, if you show up to class prepared. So that means you watch the video before class. This does not mean if I am now put into isolation because I have COVID or my family has COVID that you can teach the class. It means you've watched the video and you've come to class prepared. If there are things that you don't understand, you've emailed me beforehand and said, hey, professor, could you talk about this? 3 times all semester, you can email me and say, stuff happened, I didn't expect it to, I'm not ready today. And that's absolutely fine. But otherwise, I will assume that you are prepared for class. This will allow us to use class time more productively. If you think about how much time we have less time than you have in high school to cover a lot more material. I've been at schools that have much longer semesters than we do at Williams, and it is hard to get to all the material. There are some of you who might be taking physics or chemistry classes later, and you'll need some of the vector analysis theorems like Green-Gauss-Stokes. There will be those of you who will be going off into economics, and you will need things such as Lagrange multipliers. So there's a lot of things to cover. I also want to cover a lot of applications. I want to do introduction to statistics. I want to do mathematical modeling. I want to do linear regression. I want to do Monte Carlo simulation. A lot of these things are also great for computer science. And so in order to have time to do all of this, we need to use our time productively. So if you spend the time preparing for class, we're going to be in great shape. And you can email me either anonymously or just with your name and say, Professor, can you cover the following? When I taught differential equations in my second semester at Williams, Williams does not have linear algebra as a prereq. A lot of schools do, and I wanted to use some linear algebra, but it was not a prereq. But most people have seen 2x2 matrices. And so I asked the class, is everybody comfortable with 2x2 matrices? And there was silence. So I said, all right, nobody has any questions. Nobody wants to see a review. Okay. I was using clickers, so I asked people, I'm just curious, I'm not going to report back to the class, but press 1 if you want a review, press 2 if you don't. 43% of the class wanted a review, and not one person was willing to raise their hand. So one of the nice things about Zoom and whatnot is you can send me a private message during class if you want, saying, hey, professor, can you cover this? You can send me something before class and say, can you cover this? But odds are, if you want something discussed, there will be many other people in the class who want it discussed as well. So I strongly encourage you, take advantage of this. When I was a student, I was too timid to speak up. And I lost the opportunity to have questions asked that I would have liked answered, or to get credit for things that I know. One of the things I try to tell all of my students is eventually you will need letters of recommendation. You want to try to have at least one professor get to know you well each semester. I am happy to be that professor, happy if it's someone else. One of the best ways for a professor to get to know you is to speak up in class, talk to them afterwards. So I'm always up for taking people out for lunch or coffee or a walk or whatever. If you're virtual, we can still do it, not quite as much fun. Speak up in class, answer questions. If you answer a question correctly, email me after class and just remind me what it was. Even if you think it was something minor. Partly this is just so I get a chance to know you. Partly it's so that if I have to write a letter of recommendation, I can actually do something specific and I can use examples. These are some of the questions the student answered. And a lot of times you might think it's trivial or easy or not a big deal, but it oftentimes is a really nice subtle point, and answering that is really important. The other thing is to just prepare you for what's going to happen later in life. You want to be noticed. You want to speak up. You want people to know who you are. And so if you can get comfortable speaking up in a situation like this, you'll be more likely to speak up in other situations where it's really going to matter. I was an introvert until grad school. And when I was in grad school one day, one of my friends told me that I should run for social chair. And I looked at her and I said, normally you want a social chair to be somebody who, likes being with people, likes doing things with people. That's not me. And she said, it would be great for you, Steve. I know you would do a good job. And it was one of the two most valuable experiences I had in grad school. It would be equal to the mentorship I got by my thesis advisor. It got me out of my shell. It got me comfortable speaking. It got me to the point where I could do lots of things. And so I strongly urge you to start getting used to talking in public. It is hard at first. When I was a freshman, I had tremendous trouble talking to professors, and I was afraid that I'm wasting their time. And I always was apologetic. And it took a long time before I realized that they were in their job because they wanted to talk to students. They wanted to be here. And this is true at most schools. This is especially true at a school like Williams. So please take advantage of these opportunities. And again, if you want to do it in small groups, if a bunch of you want to come out for a smoothie or an ice cream, as the places open up, let me know. Happy to do something like that. Any questions on the content so far?
I have a question on the diagram you drew on slide 4.
Yes.
In one of the videos, you said there are partial derivatives that exist if you come along the axes, but it doesn't exist in other parts.
Correct.
I don't know if that has to do with that diagram, but do you mind answering that?
Sure. So it's related. So one of the big things is the difference between the words necessary and sufficient. So there's necessary versus sufficient. And this is why I'm upset right now that the pen is not working. If anybody has seen the movie Dodgeball, there is a nice scene where he talks about, is it necessary? About things that you may or may not do. Necessary must be true, but it's not enough to guarantee that something will happen. If you want your function to be differentiable, it is necessary that the partial derivatives exist as you come down along the axes, but it's not sufficient. So can somebody give me a necessary condition to win the Super Bowl? There's many necessary conditions.
You need a full team?
What do you mean by a full team?
Like all the players that require.
I know in football you can get a penalty if you have too many players on the field. You might be allowed to play with fewer players. It's inadvisable, especially if you're the quarterback, to have fewer people on the offensive line. But you're close. What's a necessary condition to win the Super Bowl?
It's necessary to get more points than the other team.
Excellent. Is that a sufficient condition? If you get more points than the other team, have you won the Super Bowl?
Yes.
Yes. So I would say that that is a necessary and sufficient condition. If you score more points than the other team when the time has expired, you have won. So what's a necessary condition that's not sufficient to win the Super Bowl?
You need a team.
You need a team. You need to be in the game. So if you're not in the Super Bowl, you have no chance of winning the Super Bowl. But just being in the Super Bowl is not enough. So one of the things you want to be careful about is the difference between a necessary condition and a sufficient condition. Necessary is something that must happen, but it's not necessarily enough by itself to guarantee the outcome you want. Sufficient is. And so we will talk a little bit about what is a sufficient condition to ensure that our function is differentiable. And again, my brother is an engineer. He has lots of wonderful advice. We have grown to the point where we are now friends and we understand each other, but we view the world very differently. And as an engineer, he goes, but Steve, you're spending all of your time worried about these things that never arise in the real world. Of course, my function is nice and has all these nice, wonderful properties. I don't have to worry about this. Every now and then there's something that you miss. So one of the things I want to do is I want to try to give you some reading, and I want to try to give you opportunity to work on applications. So I am a huge science fiction fan. Any science fiction fans here? Excellent. So hopefully you have read, the golden age of science fiction, The Masters. Isaac Asimov is one of my absolute favorites. Not if you want characters, his character development is terrible, but if you want ideas to play with, he has a lot of wonderful ideas to play with. And I'll be sharing an excellent essay of his on Euclid's fifth postulate. And the several that I will be sharing throughout the semester, I am choosing this one because we have just come from claiming Williams Day. And so there's many things we're supposed to be reflecting about during claiming Williams. You might think, why are we talking about claiming Williams in a math class? Your math is supposed to be this pure objective field. So if anybody wants to, you're happy to have people speak up as to why you might want to talk about this in math. I'll just say that you have to remember that mathematics is inspired by mathematicians who live in the real world. We have an axiomatic system. What is inspiring the axioms? What things are we implicitly assuming when we make the axioms? And what kind of inertia is this for change? And so I don't want to say too much more than this. I will be sending you the essay to read later. It is an absolutely wonderful essay of how easy it is to assume and not even realize that you're making an assumption. And this is something that you should always be aware of. Related to this is work can easily be misinterpreted. And just because work has caveats and conditions, just because it has context, you can't always trust that that context, as I have learned, will be propagated forward. And so when you're looking at something, always be aware of the conditions. How many of you have seen the geometric series formula? Anybody seen the geometric series formula? 1 plus x squared plus x cubed and so on, all the way off to infinity. What does this equal? Anybody remember what this equals?
Depends on the value of x. It might either.
Wonderful. So what do we need to be true about x?
It needs to be between. Its absolute value needs to be smaller than 1.
Excellent. So if the absolute value of x is less than 1, and I'll put that in red because it's fun to hit different colors, and then it will equal 1 over 1 minus x. So this is an absolutely wonderful result. But if you drop the condition that x is less than 1 in absolute value, you can make mistakes when you use it. So you have to be extremely careful whenever you use something that you use it for the desired intent. I am a huge fan of Mark Twain's witticisms. He has several that I absolutely love. One of them is, at 14, I was ashamed at my father's ignorance. At 21, I was amazed at how much he had learned. But another one is, a cat that jumps on a lit stove or warm stove will never jump on a warm stove again, nor will it jump on a cold one. For every event in life, be careful to only glean from it the lesson you should. And so again, here, the geometric series is wonderful, it's powerful. We're going to spend almost a quarter of the semester on consequences of it when we get to sequences and series. But if we forget that this is true only if the absolute value of x is less than 1, we will be led into errors. Any other questions or comments on what we have here?
So what the geometric series implies, if I'm interpreting this right, is that if you continued on potentially like to infinity with x, it would still apply that it's equal to 1 over 1 minus x.
So it would imply that if you sum every single term, you would get to 1 over 1 minus x.
Thank you.
And so it only says that if you take every single term. So any finite number will not work, but an infinite number will. So let me see if I can quickly pull something up. So I have done a bunch of slides over the years on various talks. And so, and again, this is one of the things that's nice is we have a lot of flexibility in terms of what we do. So I'm going to try to share screen right now. All right, so can people see the PDF from shooting hoops to the geometric series formula? So I will prove the geometric series formula not through the boring algebra, but by playing a game of hoops. Normally I actually bring a basketball net to class and have students play. Due to COVID restrictions, I think what I will do is I will do this, but I will bring 2 basketballs so that no one will touch a basketball used by someone else. And I think that will be sufficient to allow us to deal with this. Okay, so here's the geometric series formula. If the absolute value of r is less than 1, then the infinite sum is 1 over 1 minus r. So it's often proved by doing some algebra. Here's a quick heuristic that it's at least reasonable. And I'm going to choose a very special value of r. I'm going to take r equals 1/2. So we get 1 plus a half plus a quarter plus an eighth. And the way you can view this is imagine we have a stick figure who starts at 0. And at every 1 second forward in time, the stick figure moves 1 on the first step, r on the second, r squared on the third. So where will the stick figure be 1 second later? So where is our stick figure 1 unit later, 1 second later?
Sorry, could you repeat how the stick figure moves?
Sure. The first step, the stick figure moves 1 unit. The second step, 2 seconds later, moves r. The third step, 3 seconds, moves r squared, then r cubed, then r to the 4th. And we'll take r to be 1/2. So how much do we move on the first step?
1.
1. How much of the distance from 0 to 2 have we covered?
Half the distance.
Half the distance. How much do we move now on our next step?
1/2.
1/2. Isn't this wonderful animation? How much of the distance have we covered that's remaining in that step?
1/2.
1/2. How much do we move on the next step?
1/4.
1/4. How much of the distance remaining have we covered?
1/2 again.
1/2. So you can see every moment in time, we cover half the distance that remains. So if we were to do this infinitely often, where do you think the stick figure is going to end up?
Closer and closer to 2.
Closer and closer to 2. And it's that closer. What do we mean by closer and closer? And this is the concept of the limit. The stick
It's
figure
approaching.
is never going to be beyond 2, because at every moment in time, the stick figure is strictly less than 2. But you take any number less than 2, and eventually I go past that. So I can't end up past 2, and I can't end up before 2. So the only place that's left is I have to end up at 2 in the limit. So this is more of a geometric proof of what's going on in this special case when I equals 1/2. We will do the algebra proof later in the semester. Let's see. Are people able to see? Oh, my video is not on. Okay. Okay. Are people able to see me now? Okay. So I love Rubik's Cubes. I didn't know how to do them until a few years ago when one of my students who was very good offered to teach me. And as a math professor, there are just some things you need to learn. So if anybody wants to learn how to do a Rubik's Cube, if you want to do it with your friends, I will provide the cubes. You get to keep them. The 2x2, it takes about an hour to learn how to do a 2x2. Has everybody at least seen a Rubik's Cube? cultural extra credit. What animation movie in the past 5 years has Rubik's Cubes with the villain? Any fans of the Despicable Me franchise? Anybody know who the villain is? Which movie?
Did Victor have Rubiks Cube?
No, Victor did not. Third movie. In the third movie, the villain is a flashback to the 1980s, and he's never really gotten over living in the 80s. And so there are Rubik's Cubes there. So Rubik's Cube standard one has 6 sides. Each one has a different color. And you can turn the sides. The reason I'm doing this is this highlights how to look at algebra, and that's a huge part of the class. Frequently, the multivariable calculus is actually going to be pretty straightforward. The challenge is going to be doing the algebra. So this is one of my favorite cubes. If you look at it, well, maybe it kind of looks like it. A little bit different, but when you look at the sides of this, this is a 2x3 side rather than a 3x3. This cube looks completely different. If I try to turn the red side doesn't turn. It's much better when you can actually pass it around. This cube is essentially the same as this cube. And it took me a while to see this. I first met a cube like this. It was a little bit harder when I was visiting my daughter's class. I taught them how to do cubes. This was probably 3rd grade. And they had one like this, except it was even worse. Instead of having just a shape like this, everything was also the same color and they were different sizes as well. This is also the same as the regular cube. And the reason is it's the same is you have to hold the cube not like this so that the red is pointing at you, but you have to hold it at an angle. And if I hold it at an angle like this is now the side. And the side now turns exactly as before. If you hold it at a 30-degree angle, it's the same. For this one, rather than doing things by color, you do things based on size. As I turn it, you can see it actually starts to explode and it's no longer confined to a standard 3-dimensional cube shape. It's still the same cube, it's still the same algorithm to solve, but it looks different. This is probably the best lesson I can give you going forward in terms of how to deal with the math you're going to see in this class and beyond. The difficulty is not doing the calculus. The difficulty is looking at the algebra and finding the right way to view what's going on. And if you can find the right way to look at it, it's not so bad. Frequently, it's very easy to follow proofs line by line, or at least it's possible to follow them line by line, but you go, how the hell did they think of that? Why would you even think of doing something like this? So at one point, I might actually give you a video for a geometry lecture on ways to prove the Pythagorean theorem. And in the video you all, of course, watched for today, it talks about some ways to prove the Pythagorean theorem. Who is the most famous president in American history, at least to a mathematician?
Garfield.
I'm sorry?
Garfield.
Garfield, exactly. Why is Garfield so important?
Credited with one of the proofs for the Pythagorean theorem.
Yes, and as a Williams professor, I will not say anything about how derivative his proof might be to a standard trapezoidal proof, but he is given credit as a proofer of the Pythagorean theorem. There are lots of different proofs. This is the power of a math class. I was a postdoc at a school that came in 2nd this year in college football. Anybody know what school that is? Lost to Alabama. Yes.
Ohio State.
Nope, try again. You're close. It's not Ohio State. Do you know the full name of the school? Anybody know the full name of Ohio State? The full name is The Ohio State University. My brother used to work at MathWorks. He now works at The MathWorks. I think they added a the. Why am I saying this? Math, it's not the proof. It is a proof. There's more than one way to prove many things. Different proofs highlight different parts of the problem that are worth seeing, worth understanding. Some things generalize better than others, and it is extremely valuable to have more than one way to look at things. If I am proving something or explaining something in a way that you don't understand, rather than being frustrated, what should you ask me to do?
Do it a different way.
Do it a different way. So my freshman year, I was taking a math class and my friends and I were stuck on a problem. So we went to the math tutor and he showed us, oh yeah, here's how you do it. Boom. We just rattled off the answer. And we were just like, we don't understand anything. We don't understand even what quantities you're looking at. He goes, oh, okay. What about the following? And he rattled off a second proof and goes, okay, we at least understand the words you're using, but we have no idea about some of these results you're using. Okay. And then you had to think for maybe 20 seconds, well, what about the following? And then he came up with a third proof. Yes, okay, yes, we understand that. Okay, yes. And so there's many different ways of explaining things. Depending on how you happen to look at things, you will see different connections. My main mentor when I was an undergraduate was a physics professor, and he did a lot of his main work in experimental nuclear physics in the 1950s. He was evacuated from London during World War II. He is significantly older than I am, significantly older than you are. No computers, no internet. When he was in school, they learned trig identities up to cosine and sine of 10 theta. And he just knew them like that. And he said that there were many times in his career when he had tedious expressions and he could just look at it and see how to simplify it. He could just see what was really going on. And that was tremendously valuable. And so one of the things I really want to try to emphasize is how to look at things. There's more than one way to look at things. And if you look at things the right way, the algebra becomes very nice. I will go back and let me go back. So let's see if I can do this. Okay. So can people see the text box? It now says add the following. Can people see that? All right, first one to get this right is going to get some extra credit. What is this equal?
04600. Sorry, I don't know.
Excellent. And how did you get it so quickly?
Diagonally they crossed out.
Yes. So I'm trying to see if it will let me draw. Good. So the 2's cancel. And then the 10's cancel. The 11's cancel. The 421's cancel. Everything cancels, and you're left with just the first minus the last. Could you add them up line by line? Absolutely. But if you look at it the right way, the problem is significantly easier. And that's one of the goals of this class, is I want to try to show you good ways to look at the algebra. Cultural extra credit, anybody know what 24601 represents?
Is it the number in Les Mis?
Excellent. Who is 24601?
Is it Javert or Valjean? I forget.
It is one or the other.
Javert?
It is Jean Valjean. 24601. So when I was a graduate student, we had to demonstrate proficiency in 2 out of the following 3, French, German, and Russian. And so I knew Spanish, so for me, mathematical French wasn't too bad. But one of the things I did read for German was I actually read a little bit of Les Miserables in German and French and compared it with English and just try to learn some words. You know, you at Williams College, you are supposed to be cultured. There's many different ways to take that. You want to try to be able to speak to anybody on any subject for up to, say, 15 minutes to an hour. Later in the semester, I will talk about some applications of multivariable calculus in art. And years ago, I was being interviewed at a big firm in New York City, and I was told I would have a lunch with somebody from human resources, which is not part of the job interview. This was just a chance to relax and have my questions answered. Is this part of the job interview? Absolutely, right? Turns out the person was an art history major from Williams who had graduated a few years earlier, and I was actually applying for the job at Williams at the time. And so, you know, I am not a huge lover of the arts, but I knew enough to have a non-trivial conversation with her. And years later, I was one of only 2 people she remembered interviewing. And when she left and formed her own company, which helps people find jobs, she actually contacted me because she wanted to have connections with current Williams students and connect you to some of her other clients and also some of the other Williams students who have graduated over the years, including somebody who was one of the top people in the MBA in analytics, who actually then came to campus and mentored some of our students. So you never know where you're going to get connections. You never know what's going to be valuable. And so I strongly urge you, take advantage of being at a place like Williams. This is not the Williams Institute of Technology. Even if you want to be a science major and go off to science graduate school, wonderful choice. But there are so many wonderful classes here in so many different departments. Take advantage of the opportunities. And you will find that those are just as valuable as the technical classes. You can always learn more facts. Part of the purpose of this class is for you to be aware of what's out there so that when you see something, oh, wait a minute, this economics problem, it looks like something Miller was babbling about one day. Let me check. Everything's online. You can look up what the lecture was. You can look at the notes and you can say, okay, this is Lagrange multipliers. Okay, now I know a starting point. I know what to look for. I can now look this up and I can review. And it's much faster to review something if you already know what it is. So I am not expecting you to memorize everything. I am not expecting you to have all of this at full recall when the semester is over. Most of you are not going to use most of the material. Not a problem. What I really want to emphasize is the problem solving. I really want to emphasize how you can apply this to real world problems. Already after your freshman year, you will have enough, especially if you know some statistics and programming, to be useful. And so I used to say that if you could do programming, statistics, and probability, you would always have a job. You may not like it, but you would have a job. I can't say this because somebody sued her school when she graduated and did not get a job. And so I have to say now that you are extremely likely to have a job. She came up with a new type of discrimination, GPA discrimination, that the school was not doing as much for people with low GPAs as high GPAs. So what skills are useful? Obviously, I'm a huge fan of probability, statistics, and computer science. Writing is extremely valuable. I'm always thrilled when I have a student who's a double major math and English. It's extremely important to be able to write, or any department with a lot of writing. Being able to talk and communicate, extremely important. We are the only department left on campus, I believe, that has a required speaking task to graduate. Every math stat major has to give a technical talk to graduate. Anybody here going to be a professional mime? I would ask you to speak up, but that might be insensitive if you want to be a mime. So just raise your hand if you want to be a mime. Okay, good. So we have no one who wants to be a mime. That means you're almost really going to have to speak to people. And it's extremely useful to learn how to speak well. And so we will happy to talk about stuff like that. If any of you have interviews and want to do practice interviews, I am happy to do practice interviews with you. Going back quickly to course mechanics, homework is due at the start of class. Homework is not to be submitted late. If something is going to happen and you can't submit it on time, you have to let me know, typically at least a day in advance. Obviously, if a complete disaster happens, 30 minutes before class, I'm not an ogre. but that should not be the go-to. Most of the time, you should know when something is coming. If you think I might not be able to get it on time, you let people know. This is to prepare you for the real world, where you can't tell your boss, 20 minutes before the presentation, oh yeah, I didn't do it. That's just not acceptable. And so as long as you ask in advance, that's fine. I understand people have conflicts. We sadly do not have as many conflicts this semester as we do in previous years, but if you have things that you know about, happy to adjust the schedule accordingly. There will typically be homework due every class. Maybe not everyone, but most classes, there will be a couple of problems. This is just to keep you, current on the material so that if there are any gaps or confusions, you get feedback quickly. Homework will be graded and returned by the next class. There will be, I believe, 4 math TAs for the class, plus the Math Science Resource Center. So there will be plenty of office hours. I'm going to try to have these available at least once a day. Feel free to email me anytime, always happy to chat. And then, in terms of, the next steps, it's going to be a while before we see calculus. We have to first learn the language. And, the language is going to be the language of, vectors. So vectors in a plane, cross products, lines, equations for lines and planes, cylindrical and spherical coordinates. Once we have all of this, we'll then have the language to generalize one variable calculus. Right, we've still got a few minutes and I'm happy to stay on afterwards in case anybody has any questions. And then the other thing is, if there is anything that you want covered in class, any things that you find interesting, let me know. And I think I put in one of the emails that one year somebody wanted me to talk about bees, another year somebody wanted me to talk about the gastrointestinal system. You are absolutely welcome to try to challenge me. I'd like you to work the following in. Whatever you're interested in, this is a wonderful opportunity. By all means, look at the homework that's going to be assigned, for the lecture that you're supposed to listen to. And if you want, ask me related questions. Hey, professor, you assigned problems, 2, 5, and 8. Would you mind doing problem 6? So that I can see the details of that. And then there was a question in the chat. Do you think the ability to see a problem in mathematically useful ways is innate or developed, or a combination of the two? I would say a combination of the two, that there's a lot of things that you can be trained to do. They talk about how you can have a child prodigy in music or in math, but you don't really see a child prodigy in engineering. That engineering is more of a developed skill. There's a lot of things where you just look at it and you just see. Any young Sheldon fans here? So I am hoping that there's some intersection between the cultural stuff that I know and the cultural stuff that my kids who are in 6th and 8th grades do, and you. They are still a little bit younger than you. So I know that when one of the neighborhoods did there were 2 video games for competition. One of them was, what is it? About Us, Almost Us, what was it? Almost Human, what was it called? Anybody know what I'm thinking of?
Among Us.
Among Us, thank you. I know the game is Mafia or Murder, but my kids played that all the time, and the other one was Scribble.io, which my kids also play. And so there's going to be some intersection at least. In young Sheldon, there are 3 kids. Sheldon is the one who becomes one of the stars of the Big Bang, wonderful physicist, has some issues understanding how normal human beings interact. But in the episode we watched last night, it turns out his older brother just is a genius in automotive repair, including being able to detect where a puncture is in a tire. And it's a thing of beauty to see. We all have different skills. Some skills are valued more highly by others than other skills. But there are some things where it's just natural for some people and they just see it. Other things can really be developed over time. This is the Pavlovian response. And so eventually, if you take a class from me, if you see a product, you eventually learn whenever you have a product, you should consider taking a log. Maybe you don't take the log. If you're trying to explain how to multiply 3 and 5 to somebody in 4th grade, you don't say, well, the log of 3 and the log of 5, add them and take the anti-log, and that's the slide rule. No. But if you have a large product, the log of a product is the sum of the logs. It converts a product to sums. We just have more familiarity and experience with sums. It makes it easier to see the algebra. So there's a lot of tricks you can do to build things up. All right, so I'm gonna stop the recording now. If I can find where to stop this.